title of my talk is Too Many Satellites to Operate, How Planet Successfully Operates More than 100 sats on space using Agile Aerospace, automation, and Python. So first, my name is Kattia Flores, as you heard. So I'm the engineering manager for the Space Ops operations team at Planet in our Berlin office. And to introduce you a bit to the topic, I want to bring your attention to the background of my first slide. So that's an actual base map or mosaic built up with images from the satellites of our constellation. So why do we do this? Just to give you a bit of more context. So all of us know that things on Earth change very rapidly and constantly. So it is important to have data about those changes so that people can make informed decisions about it. So how do we accomplish that? So how did that map get to happen? So as I mentioned, we have a constellation of different satellites on orbit. We have two different constellations, and they are continuously imaging our Earth daily. And that's how we are able to gather that unique set of data for any user that may need it. So that this video is a day in the life on the constellation. So you can see like it's a ring of sensors, basically Earth observing satellites that are continuously taking picture of landmass. And that's how, you can build those maps. Talking a bit more on the constellation. So we have an heterogeneous fleet. That means we have different satellites on orbit. So two big constellations. One is the Doves and Super Doves, and I'm gonna talk a bit more about the name change there. So we have more than 100 currently in orbit, and we have launched more than 350 over time. More than 30 rockets took our sats to space. And then we have the high resolution fleet, which is 21 SkySats. So SkySats are, it's the name for our high resolution fleet. And then we were operating from 2009 to 2020, a constellation of 5 satellites called the Rapid-Eye that have been retired last year, but we still have the archive data from them available. So that just gives a really large set of data of our Earth. Okay, so we have the satellites on space. So what do we do with that? So this is the system on a nutshell. So we have the satellites, and they are taking pictures. So we need to download those pictures to the ground. So for that, we need a global ground station network. So we need antennas that will talk to the satellite, tell them what to do, and then retrieve those images that they have taken. And all of that needs to be orchestrated because it needs to work seamlessly and keep the system running. So there are systems like the scheduler or mission control, I call here, that take care of that, take care of optimizing the resources on ground, telling the antennas what to do, telling the satellites what to do, and making sure that the data comes down promptly. And once the data is down, that's not the end of the process. So the data needs to be, stored, needs to be analyzed and processed, especially the imagery. On one hand, the imagery so that it reaches customers, and on the other hand, the spacecraft produce a lot of logs and telemetry that will help us later identify if they are performing well. So it's just like managing a remote system in space. And I'm going to talk about later, like how important is that all of these, it's automated. Because as you can imagine, like, it's already complex to operate, to build and launch one satellite, but then that complexity increases when you have a larger number of them to manage. So one important thing that I want to highlight is that the way this is possible currently at Planet and since the beginning of the company is like using Agile Aerospace as philosophy on everything we do. So what this means is that we quickly iterate not only on our hardware, but also on our software. Like the image you see there is how the specific Dove satellite has changed over the years. So we have iterated that design more than 14 times in the last 5-6 years. And by doing that, we are continuously improving what is flying to space, and as a result, also like the products that we deliver. So Planet designs, builds, and launches these satellites, and then from the moment they are deployed from the rocket, then the team also operates them, and the data processing and all that part is also made in-house. So this Agile Aerospace philosophy gets applied on all part of that system. So satellite, the hardware itself, the times we will launch new satellites to make sure that the constellation, keeps the number that we need to deliver our products, and then also the software that is running on board the satellites and the software that controls all those things on the ground. So from the beginning, we made sure that we invested on designing software platforms on grounds that are built with scalability and automation in mind. Just to give you a glimpse of how fast things move, just last year, like this summary a lot. So last year we launched 5 different rockets, so 26 satellites on one of them, 2 different deployers. We also launched our high resolution sats on a different orbit. So that was challenging operationally wise, and we did that successfully. And all of these new sats and the constellation that is currently up downloaded up to 5 petabytes of data. And just a week ago, I'm also excited about this, we launched in a record-breaking rocket on SpaceX where 143 satellites were deployed altogether. So there we had 48 sats, and also want to highlight that part of the work that we do on automation allow us to also break self-record. So from the moment the satellite reaches space till it takes its first picture, we managed to do that in 58 hours, which is a record for us. Okay, so before talking about what's actually space operations and what's our role, I wanna give you a glimpse of what the satellite does. So one of our DOFs, the CONOPS, or the concept of operations, is pretty simple. So whenever the satellite sees Earth from space, it's gonna take pictures. And whenever it's in view of a ground station, it's gonna download data. Whenever it's not doing either of those 2 things, then it will do maneuver, such as that they space along the orbit, so that they act together as a more distributed sensor. And the important thing here, distinctive to other ways of doing space operations, is that we don't do 24/7. So our team is not sitting 24 hours in front of, monitoring how each satellite is doing. And that's possible because of automation. And I'm gonna touch that later. Yeah, so coming back to this graph, so all these things need to happen continuously, and it's impossible to do this with a human in the loop in all parts of the system. So as I mentioned before, the mission control is the system that is in charge of talking to the satellite and orchestrating the data that needs to go to the ground stations and the antennas. And then we have inbuilt or in-house built tools that will optimize how those allocations are done. So all these parts of this system diagram are fully automated. So now going into what's a space operation. So what my team responsibility is, as I said, from the moment the satellites are deployed on space, we have this next phase called commissioning, where we make sure that the satellites are in a stable place so that they are not tumbling, because I have one model here, because when they leave the rocket, they will be like rotating. We make sure that they have a stable attitude and control attitude, that the solar panels have deployed, that they have enough power to perform nominal operations. What's nominal operations is that the satellite is able to start taking pictures and downloading data. So after that phase is complete, comes the monitoring phase. So we want to make sure that every day all those satellites are performing as we expect them to. That's obviously an ideal scenario, and it's never quiet. So there are always there will be some anomalies that will happen on some satellites. So we want to make sure that we see them timely and that we address them timely. And this becomes more complex as the number increases. And then we, as part of the Agile philosophy, we will also test on orbit continuously. So if there's an upgrade that we think will improve performance, then we would test that on orbit. So that we call that on orbit experiments. Then we'll perform software upgrades when we have tested them on ground and feel confident that we want to put them up on space on all the satellites. And obviously, each of the satellites will reach an end of lifetime, so that's the retirement. But even after that, all the data that on performance of that satellite will inform future analysis. So analysis on forecast models, degradation models that we can use and iterate on next designs. Focusing more on monitoring and anomaly debugging. So here's where automation plays a big role. So obviously, we didn't have from one day to another more than 100 sats in orbit. There was some point in time where we started with 10 satellites, definitely less than what we have now. Back then, mission control, so the system that orchestrates all the data that will go through to the satellites, the commands and the configuration control. So that was already built with automation in mind. So back then, the role of space operations was to keep the satellites healthy and gather as much data and experience on what we need to do to scale. So this was this is an example of how the operator would see data from the satellite. So basically, a satellite is like it's like a computer. So it's a computer. So it will have telemetry from different parts of the subsystem. You know, like is the CPU turning on, like current data. So it's a lot of data that we need to parse daily to make sure that that satellite is doing fine, that system is doing fine. So back then there was a script that will compile all the different errors or signatures per satellite, and then there was more involvement of an engineer to actually go and look through that data. But obviously, when we started launching more satellites and growing the fleet, that was not scalable. So we had to do that per satellite, and for 10 satellites might work, but for 100, then you would need way much more people, and it's definitely just not efficient. And as well, as I mentioned, as we had 14 iterations of the same satellite, so the performance data will change between iterations. So that's also another thing to consider. So definitely there was the need for more, for smarter metrics and smarter ways of making sure that the constellation was performing well. So there was a point where there was a paradigm shift. So instead of looking at a satellite as a unit, we switched to look at the constellation as a group. For doing that, we decided to shift focus to fleet-wide problems. So we started generating metrics that will tell us, okay, as a group, all these satellites together, what are they supposed to deliver? So for example, all of them, we expect them to take a certain amount of pictures, and those pictures mean a certain amount of bytes. So that's a way of knowing, as a system, is that constellation doing fine? So that's one of the things we shifted to. And then the second is we wanted to make sure that we only put engineering effort on anomalous sats. So we want to make sure that we just perfectly pinpoint like where are the problems and pay attention to those. So for identifying anomalies on specific satellites, we moved heavily to rely on metrics. So we have all this data, and we implemented scripts based on Python, where we would also, with operator experience over the years, we would identify these numbers or thresholds or trends on the data that would tell us that a satellite has a problem. That was the first step, and then once we had that in place, we could implement automated detection. So there will be a job that will look at that data and then trigger a detection, an alert for an engineer, or even a reaction to that anomaly. Outside the identification of anomalies, there is also, like, if we already have that data, there are ways of increasing the system availability and capacity. And I'm going to mention an example later. So this is a very simple diagram of what that looks like. So in the square here are the sources of data. So mission control gathers data from the satellites. The satellites are going to download telemetry. Telemetry is just like health data from different subsystems, logs of what's happening on board, and data of where the satellite is. So all that data lives on tools and systems on ground that we build in-house, that we have APIs for. So basically what we do is query that data from those APIs, and we wrote different scripts with different focuses, and we call them mission metrics or metrics reports. And each of those reports will run at a cadence that we need to, and like aggregate records per we see fit. So for example, if we want to detect if a satellite is not generating enough power, so we want to aggregate not over a day, but in a shorter time of period. And all of those results like generate records, and those records then get stored. And from there, we have different ways of viewing the data. So it might be useful to see that data visually, for example, like on charts or trends, or we could also directly trigger other automations that will like check, for example, on deviations on the trend of the data, and then tell us that something has changed. So it's really, it opened a lot of possibilities. And the system on ground also allows us to expand on it. So we could add more reports, and the system is built for that. So focusing a bit on the automation detection and reaction, which was a really game changer for us. So that's basically, yeah, a set of Python scripts that are consuming data from the different APIs or from the aggregated metrics, and then they are triggered by scheduled jobs, and then they will send alerts to us. So that replaced the role of an operator. That was the typical or the stereotype some years ago. So one specific example of that, it's managing the duty cycle. So duty cycle is how many images a satellite will take in a given day. So that depends on how much power the satellite has, and there are variations of the sun illumination that the solar panels will have across the year. So that's definitely something that can't be done manually. So each sat will go through different phases because they are on different orbits. So we needed to automate that. So we have that data coming through. So we have the telemetry from the solar panels. We know what the trend of the solar illumination would be. So we take those inputs, and then there is a job, which is the Python script, that will compute what's the maximum duty cycle that satellite can have based on that information. And then there is another job that works together with this one that checks if the satellite is triggering a flag because it doesn't have enough power. So if that happens, it will adjust the duty cycle accordingly. So that's just one example of many that we have implemented that allows us, to just like be hands off on optimization. Okay, and then what's next? So we have all this data aggregation and data analysis already in place. So what we are looking at next is exploring more machine learning, for example. That could allow us to, instead of be reactive, do the prediction part. So maybe we can detect an anomaly before it happens, or we can even discover trends that we haven't seen or noticed before, because it's just like a lot of data to go through. And then eventually move to autonomous operations. So where there's absolutely no human in the loop, and then the system takes care of predicting and reacting. But yeah, that's future work. I had this video just abstracting out of what we do in operations, and it's the impact of having Earth observation. But while that plays, we can also go ahead and move to questions. This is a timeline change of the Amazon with images from our satellites of over 3 years of data. So, like, you can clearly see how the landscape changes. Thanks, everyone. So if anyone has questions, and if you're excited about what we do, check our careers page, because we are hiring on different roles.
We've had a few questions. One from Danielle saying, where did your passion for space and engineering start?
Yeah, so actually my background is telecommunications engineering, and there I got into satellite communications, and I knew that was something really exciting, and I decided to shift towards that. So I think that was the trigger for me. And really, space is a multidisciplinary area of work. So we have people from all different backgrounds. And I think one of the great things of doing everything in-house is that you have all those different engineerings working together.
Alexandra said, I'm really curious, what's the biggest incident you've faced and how it was solved considered limitation in communication with satellites?
Well, I don't think there is one big incident. So we see different anomalies across time. And what we try to do is, again, like give that feedback of what we observe in orbit to ground so that the next design of our satellite will account for that failure or error. And there is, as I said, we have a global ground network of antennas. So we will scale that as we need to make sure that we are downloading the data or communicating with our sats at the pace we need to.
We've got one last question again from Alexandra. How do you handle legal filming restrictions over specific areas?
Yeah, so our satellites, the images they take in our Dove fleet have a resolution from 3 to 5 meters. So that doesn't really allow you to see a specific person, for example. So if that's the privacy concern. So
Okay,
1 pixel, it's equivalent to 3 to 5 meters.
Is there a need or plan to detect anomalies in real time?
We do actually. So while the satellite is in contact with one of the antennas, we have automated scripts that will check if there's something anomalous on board and will correct it right away. But also the system is built such that we have some bandwidth. So there are no errors that will happen immediately that will be fatal. So we can afford to look at them after some time.
Thanks a lot for the talk. It was super, super interesting.